Myself, Dr.CR Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the optical properties of European 3+ dope lead fluorophosphate glasses for red laser applications. This is one of the topic from the laser glass spectroscopy. So last and previous session we have discussed about the spectroscopy properties of samarium 3+ ions in lead fluorophosphate glasses. So today class I am going to discuss about the optical properties of European 3+ dope lead fluorophosphate glasses for lead laser applications. In this today talk, outline of the today talk is on the introduction. First, introduction of the European 3+ dope lead fluorophosphate glasses. Next, experimental methods and techniques of the European 3+ dope lead fluorophosphate glasses. Next, results and discussion of the European 3+ dope lead fluorophosphate glasses. Finally, conclusion or summary of the European 3+ dope lead fluorophosphate glasses for red laser applications. These are today we are going to discuss about the optical properties of European 3+ dope lead fluorophosphate glasses for red laser applications. So in visible laser applications, we are using the European 3+ dope lead fluorophosphate glasses. Next, coming to the introduction. Motivation of the rare earth ions. So main motivation of the rare earth ions is, see here, periodic table is the complete periodic table of the rare earth elements. See here, lanthanide ions is starting from the cerium to lutetium. So in this cerium, prismodium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, yttrium, lutetium. Today I am going to discuss about the europium dope lead fluorophosphate glasses. This is one of the rare earth elements in the completely from the among the 14 lanthanide are rare earth elements. So from the importance of lanthanide, see here, this is the complete 0 to 14 elements of the lanthanide ions are rare earth elements. In that, we are going to discuss about the European 3+ dope lead fluorophosphate glasses. So in the case of European 3+ ions, what is the importance of lanthanum ions? So first importance is shielding of 4f orbital, because this rare earth elements are lanthanum ions is belongs to the 4f orbital. That means lanthanum ground state is 4f of n is equal 0 to 14. So this completely belongs to 4f orbital elements of the rare earth ions are lanthanide ions. Next, similarly, chemical properties. Next, electrostatic bonding and variable geometry. These are the importance of the lanthanum 3+ ions. Next, coming to the what are the important optical properties of the lanthanum ions. So luminescence from the F transition to F transition, because this European 3+ ions is mainly belongs to the F orbital elements, that means F black elements. So characteristics of the emission for each ion, it will shows the different characteristics of the each and every rare earth ions. Next, narrow emission line, high chromatographic purity. These are the one of the important property of the European 3+ ions. Next, emission color is not very dependent on ions environment. So this is also one of the important emission color. That means it depends on the emission is not very dependent on the ions environment. Next, large Stokes shift. That means Raman shift is there. That is, it depends on the rare earth ions. It will be shift the some Stokes shift also having the in the case of European 3+ ions, large Stokes shift is having. Next, direct excitation in 4f levels is not efficient. Next, sensitization luminescence is preferred. Next, long excited states lifetime is having the long excited state lifetime. That is why so European 3+ dope glasses always having the milliseconds range, 4 or 5 in the range of 2 milliseconds to 5 or 6 milliseconds. It depends on the host materials. So European 3+ dope, these are the fascinating optical properties of the European 3+ dope lead fluorophosphate glasses. Next, coming to the main introduction of the European 3+ dope glasses. First, rare earth elements. So already we discussed, same here we are discussing 4f and 5f black elements and their unique trivalent state of 4f and electronic configuration. So that is shielded by 5s2 and 5s6. So you see the orbital electronic configuration, the European 3+ dope, that means rare earth elements, it always is belongs to the fourth black elements, 4f black elements, and the electrons shielded by the 5s2 and 5p6 electrons, and so many advantages. Next, coming to the glasses. Glass is an indispensable photonic platform material due to its high optical transparency and thermomechanical strength and ability to shape into a almost unlimited range of geometrical structure and composition. So glasses we can fabricate the or synthesize the bulk material to we can draw the optical fiber also. In the case of glass material, that is the this ability to shape into any almost unlimited range of geometrical structure and depends on the composition. We can fabricate the different varieties of glass materials. Next, what are the applications of glasses? So large gain media. So laser glasses having the laser gain media is very important. Next, fiber amplifiers and optical components and medical accessories and massive structures and entertainment and etc. These are the few applications of the rare earth doped elements. Next, rare earth ions in the glasses. So many applications: laser gain media, optical fiber amplifiers, etc. These are the important applications for the laser glass materials. So many applications. Among the many applications, the laser gain media is one of the important application, and optical fiber amplifiers also one of the important application for the European three-phase dope lead fluorophosphate glasses. These are the introduction of the general introduction of the European three-phase dope lead fluorophosphate glasses. Next, coming to the glasses doped with lanthanum ions, that is lanthanum triple ions, are used for solid state lasers, solar concentrators, and optical detectors, and waveguide lasers, and optical fibers for fluorescence display devices, etc. The contemporary research focus on the lanthanum three-phase doped glasses is not only limited to infrared optical devices, but also there is a growing interest in visible optical systems. Not only infrared region, and also it can be interest in the visible optical systems also useful for the European three-phase dope lead fluorophosphate. Next, fluorophosphate glasses. So this glasses combination of fluoride and phosphates. Fluorophosphate is the combination of fluoride content and phosphate content. That will be belongs to the fluorophosphate glasses. See, own better chemical stability and a less complex fabrication route than those of fluoride glasses. Next, coming to the among oxyfluoride glasses, the fluorophosphate glasses have been of great interest because of its high optical quality. It's having the high optical quality. That means highly transparent, low melting temperature, relatively high density, and good chemical durability. These are the important properties for the fluorophosphate glasses. It is desirable that the laser glass has a large emission cross section. If you see the laser glasses, if you see the European three-phase doped lead fluorophosphate gas doped with that kind of laser glasses, it having the large emission cross section, long lifetime, long fluorescence lifetime, that is very large emission lifetime, and narrow emission bandwidth. These are the important characteristics for the laser glasses. There is a fluorophosphate laser glasses. These are the important application. That is, one is the large emission cross section. It's having the large emission cross section, longer lifetime, and also narrow emission bandwidth. Next, coming to the in fluorophosphate glasses, we are used modifiers is potassium oxide (KTO) is the best modifier to achieve good properties. Also, KTO is often used for modify for the low field strength cation, where K plus improves the mechanical properties which are prerequisite for a good laser glass. So it is the one of the important good laser glass we can use at that time. This is the improve the mechanical properties, that is very important. So whenever improve the mechanical property in the glass material, we need to use for the potassium oxide. We need to use as a modifier potassium oxide. Then only we can get the good laser glasses. Next, aluminum oxide. This often used to modify the glass structure which improve the chemical stability. If you are using potassium oxide, it improves the mechanical property, mechanical strength. But if you are using aluminum oxide, it improves the chemical stability and physical properties. These are the one of the unique property whenever adding the aluminum oxide into the host material. So this is one of the important properties. Next, coming to the in the addition of metal oxides such as sodium oxide. So whenever host glasses we are using a sodium oxide, it reduces the viscosity of the melt towards lowering the melting temperature. So it will reduce the melting temperature from high temperature to low temperature. Whenever adding the sodium oxide, Na2, whenever adding, it can be reduce the melting temperature from, if suppose 1400 degrees centigrade to 1200, like that, it will be reduce the melting temperature, and can also control the tendency towards crystallization. So it will be control the tendency towards the crystallization also, it can be reduced. So next one is the presence of lead fluoride. So PbF2, it improve the emission cross section of the fluorophosphate gas. Whenever in the host material fluorophosphate gases doped with PbF2, that means modifier, we are using as a modifier as a lead fluoride content. It improve the emission cross section of the fluorophosphate gases. Moreover, the addition of lead fluoride is decreases the host phonon energy and thereby suppress the non-radial decay loss. Whenever the lead fluoride content will be in host glasses, it will decrease the host phonon energy. That means phonon energy will be decreased. That means low phonon energy. Thereby, it suppress the non-radial decay loss. At the same time, emission cross section will be improves or increases. So this is the important parameter in the fluorophosphate gases. Next, coming to the europium 3+ doped glass. So among the lanthanum ions, among the 14 lanthanum ions, europium 3+ is the one of the best candidate to be used as a spectroscopic probe, investigate the local structure around lanthanum ions in condensed matter physics. In the condensed matter physics. So this is because the lower lying energy level scheme of europium 3+ ions is simply on the transition between 7f0 to 5d0. So that is the transitions of the europium 3+ doped glasses, transition in between the 7f0 to 5d0 non-degenerative levels, inconvenient to apply the fluorescence line narrow technique to analyze changes from site to site through energy level scheme analysis. So as per the energy level analysis scheme, we can change the fluorescence line narrowing technique from 7f0 to 5d0. So next, also europium 3+ doped materials are frequently used in photonic applications. That means the photonic applications means we can use for laser source, the semiconductor device applications, and optical fiber amplifiers. So many applications we can use for the europium 3+ doped because it's one of the important applications in the photonic applications. As a red emitting phosphorus for field emission technology due to their narrow and monochromatic emitting nature of europium 3+ ions due to 5d0 to 7f2 transition. So main transition is the 5d0 to 7f2 transition. So that way they are using for the emission technology. It's emitting phosphorus for the field emission technology due to narrow and monochromatic emitting nature, since it's having the transition from the 5d0 to 7f0 transition. Next, coming to the material selection. So before going to prepare the glass sample, we need to select the materials. So the present material section highlights the facts or advantages behind the selection of fluorophosphate glass system for the present study. In present study, we focused on the optical properties of europium 3+ doped lead fluorophosphate glasses for redLaser applications. So europium 3+ doped exhibit the very visible region red emission. That is why it can useful for the redLaser applications. We can use for the europium 3+ doped fluorophosphate glasses. Next, what are the chemical composition of the present study? See, in the present study we used fluorophosphate. So phosphate, 44 mole percent of phosphate, P2O5 phosphorus pentoxide. Next, modifiers is 17 K2O potassium oxide, 9 aluminum oxide, and 24 minus X lead fluoride, and 6 mole percentage of sodium oxide. Next, X mole percentage of europium oxide. That X mole percentage is varying from 0.1 mole percentage to 2.0 mole percentage. So hereafter referred as each and every sample lead fluorophosphate europium 01 means this 0.1 concentration. If 0.05 means 0.5 concentration. If 10 means 1.5 mole percentage of europium 3+ ions. If europium 20 means 2 mole percentage of europium 3+. concentration. So these are the chemical composition of the European 3 doped lead fluorophosphate glass system. Next, coming to how experimental technique, how prepare the glass sample. So this is a important technique or unique Q and conventional technique is melt quenching technique. It's a melt quenching technique we are using to prepare the glass materials. Initially, you are taking the above mentioned chemicals. We need to measure by using the optical balance. Say weighing accurately, we can take from 8 gram to 25 grams. After taking the chemical composition, we have to put into the agate mortar. This is the agate mortar. We can crush the powder, fine powder. We can crush the powder by using the agate mortar. We can grind the well thoroughly grind and we have to make it fine powder. Otherwise, we can use the agate mortar to, and also we can use for ball milling also. Ball milling one is the machine to crush the chemical composition and we have to make a fine powder. So that is a bulk powder in the size will be little bit more in micron size that we can do. Nano size we have to crush. That is fine powder you have to make it. Then after making the fine powder sample, we can keep into the platinum crucible. This is a made up of platinum. In this platinum crucible, we need to pour into that chemical composition. Next, cover with the lid. That is made up of platinum. Then that chemical composition we are keep into the electrical furnace at the temperature, melting temperature of 1060 degrees centigrade. In the duration of melting duration time is 90 minutes, means 1.5 hours. We need to keep at the temperature of 1060 degrees centigrade. Next, after melting the glass sample, we need to pour the preheated brass mold. It's already preheated brass mold. That is temperature will be 350 degrees centigrade. So after that duration also 15 hours. So after pouring the next keeping the annealing furnace for annealing, that means 350 degrees centigrade. Then after cool down to the room temperature, we need to take it out in outside at room temperature. Then we are going to cut the glass samples and well polished. Then after well polished sample, we have to send into the different calibration technique. Initially, we need to measure the XRD technique because XRD measurement used to measure the whether prepared glass sample will be shows the glassy nature or crystalline nature. So in our present class, it shows the broad peaks. Each and every peak is showing the broad peak. That is why it shows the very glassy nature. It's not having any crystalline nature. That is why our prepared sample completely glassy nature. So after preparation of the glass sample, we need to measure the different characterization techniques. So first initially Raman analysis. So Raman analysis measured by using the Raman spectrum is obtained in backscattering geometry. Used Raman spectrometer is LabRam HR800 with the 540 nanometer of argon laser as an excitant source. We are used to measure the Raman analysis. Next, absorption spectra, second one. So in this Raman absorption spectra, I measure the Perkin-Elmer spectrometer. That instrument model number is lambda 950 in the wavelength range of 250 nanometer to 2500 nanometer. Next, after that, we can need to measure the fluorescence and decay time is lifetime measurements. In the decay time and fluorescence measurements carried out by using the fluorescence and lifetime measurements were carried out by using the Joby by fluorolog 3 spectrophlorimeter using xenon arc lamp radiation source by exciting the samples with 394 nanometer. So the xenon arc lamp we are using the wavelength is 394 nanometer used to measure the fluorescence as well as decay time measurements. Just all the measurements is carried out are made at room temperature. So these are the experimental technique methods for different characterizations: Raman spectrum, absorption spectra, and fluorescence and lifetime measurements. Let's coming to the first Raman spectrum. See by using the Raman spectrum, we are analyze the Raman spectrum. See here wavelength versus Raman intensity. See here in this Raman spectrum, we can observe the different Raman peaks. So 1, 2, 3, 4, 5, 6 peaks. Among the 6 peaks, this is the maximum intensity peak at the 1120 centimeter inverse. We are getting the maximum vibrational band. This band shows the phonon band of the present studied European filterscope lead fluorophosphate glasses. So see here, it is known that the phonon energy of the host can be defined as highest vibrational energy of the host which can be measured as from the Raman spectrum. So highest vibrational energy. So among the 6 Raman intensity peaks, we are maximum highest intensity peak we are getting at 1120 centimeter inverse. So this is the present classes phonon band. So phonon energy. This is the maximum phonon energy of the present class. It shows the 1120 centimeters, which is the lower than phosphate classes. Phosphate classes having the 1200 to 1350 centimeters. Next, borate classes 1340 to 1480 centimeters. But in the fluorophosphate class, we are getting less than that. Phosphate and borate. So this is the fluorophosphate class. Our present study class is European triple dope lead fluorophosphate classes. So we are getting the vibrational band or phonon energy band at 1120 centimeter inverse. The low phonon energy of the glass reduce the non-radiative energy loss due to multiphonon relaxation and thus yields the high fluorescence quantum efficiency. That is why whenever the phonon energy will be decreasing, it's automatically fluorescence quantum efficiency will be increases. So in the present class, phonon energy we are observed at 1120 centimeter inverse. This is the European triple dope lead fluorophosphate classes. Next, coming to the optical absorption analysis. This is the optical absorption analysis of the European triple dope lead fluorophosphate classes, UV region as well as near infrared region. So from here to 350 nanometer to 750 nanometer, this is the UV visible range. From 800 nanometer to 2500 nanometer, this is the near infrared region. So here different absorption transitions takes place from 7F0 from ground state to different excited states. So European triples doped fluorophosphate classes of ground state energy is transition is 7F0. These are the remaining excited states from ground state to different excited state of European triples science. See here optical absorption spectra of lead fluorophosphate glass, the 1 mole concentration of the European triples ion here taken. So this glass ranges from 350 to 2450 nanometer along with assignments of the absorption bands for the excited level from the ground level European triples ion as shown in the figure. From the absorption spectrum from figure 3, it is clear that 13 absorption bands are observed. Here among the visible and near infrared region, we are observing the 13 absorption bands from the ground state to different excited states. And those are almost occurring in the ultraviolet and visible region, and also 2 more bands in the infrared region. So among the 13 bands, we are observing the visible region and the ultraviolet as well as near infrared region. This is the absorption spectra of the European triple dope lead fluorophosphate classes. Next, coming to the by using the optical absorption spectra only, we need to calculate the JO. JO means judo of rate intensity parameters. Judo intensity parameters calculated by using these references 8 and 9. And also by using the 7th reference, we have calculated the oscillator strength, F experimental oscillator strength and F calculated oscillator strength. By using oscillator strength, we are calculating the omega 2, omega 4, omega 6. These 3 intensity parameters, we can say the judo of rate intensity parameters. By calculating the intensity parameters, here see the omega 2 value is 4.94, omega 4 is 5.64, omega 6 is 0.88. Among the 3 intensity parameters, omega 4 getting the larger value than the omega 2 and omega 6. That is why it shows the higher rigidity of the medium and higher covalence around the European triples ions. So omega 4 is more. So omega 4 is greater than next omega 2, next omega 6. This is the order follows the JO intensity parameters. So omega 4 is the more, next omega 2, next omega 6. It shows the higher rigidity of the medium and higher covalence around the European triples ions. In this table shows the different host materials. We are comparing with different European triples dope fluorophosphate classes. So here next TR is the radiative time, radiative decay time and the order of the intensity parameters. Next, coming to the excitation spectrum. In this excitation spectrum, the excitation spectrum we excited 613 nanometer of lead fluorophosphate of 1 mole constant of European triples. The inset shows the phonon sideband spectrum. So the inside diagram shows the phonon sideband spectrum. The PSB is a phonon sideband spectrum. So this is the red peak. This belongs to the phonon sideband. So this excitation spectrum, the excitation spectrum of red fluorophosphate glass obtained by monitoring the emission at 630 nanometers shown in figure. From the excitation spectrum, high energy transition have been located and assigned as from 7 ground state to different states of excited state of the European 3 plus ions. Among this 7F0 to 5L6, this is the 7F0 to 5L6. This transition found to be most intense, which will be excited to record the emission spectrum of red fluorophosphate gas. Though this emission is the highest intensity excitation band, that is 394 nanometer. This is used to measure the emission spectrum. This phonon energy of the any host matrix can also be determined from the phonon sideband PSB spectrum. The PSB spectrum of red fluorophosphate gas is shown as a inset figure. Okay, this is the excitation spectrum. Next, coming to the emission spectrum. This is the emission spectrum of red fluorophosphate glasses. See here, this is the emission spectrum of European 3 plus doped glasses for a different concentration. The insert shows the variation of emission intensity ratio R with respect to European 3 plus concentration. See here, the insert diagram shows the concentration versus intensity of the ratio, ratio of R, that is emission intensity ratio. So this is the emission spectrum of the different concentration of red fluorophosphate glass. Here exciting using 394 nanometer. See here, different concentration from low concentration 0.1 mole percentage to 2 mole percentage of European 3 plus ions. See here, this is the emission transitions of the European 3 plus doped glasses. We observe in different color regions. The green, next deep green, next yellow, next orange, red, deep red, and deep red. These are the different emission transitions of the European 3 plus doped red fluorophosphate glasses. Next, obviously, the emission intensity of observed transition increases with increase of European. See here, this increase in the concentration, the European ion concentration intensity also increases. That is, your emission intensity of observed transitions increases with increasing of European 3 plus ion concentration. This is the emission spectra of the European 3 plus doped red fluorophosphate gases. Next, coming to the emission spectra only, we need to calculate the stimulated emission cross section by using this formula sigma psi j to psi dash j dash by using lambda p4 by 8 pi cn square into delta lambda effective by IARE. Okay, radiative property, that is radiative transition probability AR value. By using this formula, we can calculate the stimulated emission cross section of the European doped red fluorophosphate gases. These are the observed emission transitions from 5D02. That means excitation to emission transition 7F0, 7F1, 7F3 to 7F3, 7F4. These are the different transitions. Next, these are the different wavelengths from the by using full width of medium delta mu and branching ratio beta. These are the calculated by using these formulas. So these are the emission spectra of the European 3 plus doped red fluorophosphate gases. Next, coming to the decay time or lifetime measurements of the European 3 plus doped red fluorophosphate gases. See here the time versus normalized intensity. These are the different concentrations of the European 3 plus doped red fluorophosphate gases from concentration from low concentration 0.1 to 2.0 mole percentages. They are exciting at 394 nanometer. The monitor the emission at 613 because the European 3 plus doped gases it exhibit the emission at maximum intensity emission at 630 nanometer. It is 613 nanometer. That is why you are monitoring the emission transition at 630 nanometer, exciting with 394. You have to measure the emission lifetime measurements by using this formula. This is the tau experimental lifetime integral of t into I of t dt by integral of I of t theta. By using this formula, we can calculate the lifetime measurements of low concentration. 1 mole percentage is varying from 2.14 milliseconds and 2.28 millisecond, 2.29 and 2.32 milliseconds. This is 2 mole percentage of European 3 plus doped glass lifetime is 2.32 milliseconds, which is almost independent of the European 3 plus concentration. This shows that the probability of the non-reactive energy transfer between European 3 plus ions in red fluorophosphate gases is negligible because this is independent of the European triplet ion concentration. This is almost all the concentration similar lifetime measurement, that is 2.14 millisecond to 2.32. So variation will be very less. Next, coming to the partial energy level diagram of European triplet ions in lead fluorophosphate glasses. This is the absorption transition of the European triplet ions. These are the emission transition. We are exciting with from ground state 7F0 to different excited states. This is 394 nanometer we are exciting. This is a non-reactive decay and non-reactive decay, different non-reactive decays, and it will be showing the different emission transitions. This is 1, 2, 3, 4, 5, 6, 7 emission transitions we are getting. One is a green region 536 and a deep green region 554 nanometer, and a yellow region 579 nanometer, and orange region 592, and red region 613. This is the highest intensity region, red region, and a deep red and red. So these are the 613 is the we are getting the highest intensity of the European triplet dope lead fluorophosphate. That is why we are using for red laser applications. We are using for the European triplet dope lead fluorophosphate glasses. So yes, can be seen from the figure. They exist of the large energy gap in between 470 nanometer between the 5D0 fluorescence and next lower level of 7F6. Therefore, the non-native transition rate due to multipolar relaxation for the 5DG level is very small. The difference between tau extremity and tau radio lifetime may be due to the European triplet to European triplet ion interaction. That is why you are getting the lifetime will be almost similar, independent to the European triplet ion concentration. This is the partial energy level diagram of European triplet to lead fluorophosphate glasses. Finally, summary or conclusion of the present study. In summary, the lead fluorophosphate glasses doped with the European triplet ions have been prepared and studied through the vibrational and spectral properties. And Raman spectral analysis we have studied, and absorption studies we have studied, and fluorescence and lifetime measurements, that are the spectral properties have been studied in the European triplet dope lead fluorophosphates. Next, the geo intensity parameters have been derived for the 1 mole concentration of European triplet dope lead fluorophosphates by analyzing its absorption spectrum. A relatively higher value of omega 4 indicates the higher rigidity and or higher asymmetry around the European triplet ions in the present host materials. So next, large stimulated emission cross section and higher branching ratio and quantum efficiency are usual characteristics of the good material for getting efficient laser light. So efficient laser light we have to get means we need to have the higher value of stimulated emission cross section, higher branching ratio. At the same time, quantum efficiency will also very high. Next, decay rates of the 5D0 level of European triplet ion in the present classes are found to be single exponential. Decay times increases with increase of European ion concentration. Next, overall, the strong red emission recorded at 630 nanometer. So overall, in the present study, we are getting the European triplet red emission around at 613 nanometer, corresponding to the transition is 5D0 to 7F2 transition. European triplet ions of 1 mole concentration of the European triplet dope lead fluorophosphates. So it appears a good candidate for lead laser source applications. So that is why you finally the optical properties of European triplet dope glasses is used for the red laser applications because it exhibit the wavelength in the red region at the wavelength of 613 nanometer. It belongs to the red color region. So that is why we are used as a good candidate for red laser applications. We are using for the optical properties of European triplet dope lead fluorophosphate glasses. So these are the present study glasses cited references. This is the different references. This present study mainly is published in the Journal of Material Chemistry and Physics. This is one of the my publication. These are the Judo update intensity parameters. By using these references, 8 and 9 references used to calculate the intensity parameters. These are the different references or citations of the present study. Next, thank you. So next class we will continue in the other topic. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.